In 1972 and 1973, NASA launched two ambitious spacecraft, Pioneer 10 and Pioneer 11. Their mission to explore the outer solar system. These robotic explorers were tasked with studying Jupiter and Saturn, beaming back unprecedented data about these gas giants. The Pioneer spacecraft were marvels of engineering, equipped with scientific instruments to study magnetic fields, solar wind, and cosmic rays. They carried golden plaques, messages from humanity to any extraterrestrial intelligence they might encounter on their interstellar journeys. After successfully completing their primary missions, the Pioneer spacecraft continued their journey into deep space. Scientists expected them to maintain a predictable trajectory, gradually slowing down due to the sun's gravitational pull. However, as scientists tracked the spacecraft's signals, they noticed something unexpected. The Pioneer spacecraft were not slowing down, as predicted. They were experiencing a tiny but persistent acceleration towards the sun. This unexpected behavior baffled scientists and marked the beginning of a scientific enigma known as the Pioneer Anomaly. The Pioneer Anomaly was first noticed in the early 1980s when scientists observed discrepancies between the predicted and actual trajectories of the Pioneer 10 and 11 spacecraft. Initially, these discrepancies were dismissed as minor errors. However, as the spacecraft traveled further into space, the anomaly persisted and became statistically significant. The discrepancy was tiny, just a few millimeters per second over a year. But over vast distances, this tiny anomaly added up, causing a significant deviation. Scientists meticulously checked their calculations, accounting for all known gravitational forces. Yet the anomaly remained, suggesting an unknown force was acting on the Pioneer spacecraft. Faced with the perplexing Pioneer anomaly, scientists initially explored conventional explanations. They meticulously re-examined their models of the solar system, looking for any gravitational influences they might have overlooked. One hypothesis suggested that the anomaly could be explained by the pressure of sunlight, known as solar radiation pressure. However, calculations showed that while solar radiation pressure does exert a small force on spacecraft, it was far too weak to account for the observed anomaly. Another possibility was that the spacecraft were leaking gas, creating a tiny thrust that was pushing them in the opposite direction. This theory was also ruled out after careful analysis of the spacecraft's fuel systems and thermal behavior. As scientists ruled out one conventional explanation after another, the Pioneer anomaly deepened. It became clear that something more intriguing and perhaps more fundamental was at play. The anomaly hinted at the possibility of new physics, unknown forces, or even a flaw in our understanding of gravity itself. As the Pioneer anomaly resisted conventional explanations, scientists considered radical hypotheses. One hypothesis proposed the anomaly was caused by dark matter's gravitational pull. Dark matter, a mysterious substance, makes up a significant portion of the universe's mass. It doesn't interact with light, making it invisible, but its gravitational effects are observed. Could the Pioneer spacecraft be interacting with a dark matter halo around our solar system? Section 5, Beyond Our Dimension, Exploring the Extra Dimensions Hypothesis. Another captivating hypothesis proposed that the Pioneer anomaly could be evidence of extra dimensions beyond the familiar three spatial dimensions we experience. String theory, a theoretical framework in physics, suggests the existence of extra spatial dimensions curled up at extremely small scales. According to this hypothesis, the Pioneer spacecraft might be experiencing a gravitational pull from objects or forces residing in these hidden dimensions. The idea of extra dimensions, while mind-boggling, has been explored by physicists as a way to unify gravity with other fundamental forces. However, the extra dimensions hypothesis, like the dark matter hypothesis, remains highly speculative. There is currently no experimental evidence to support the existence of extra dimensions, and it is unclear how they would specifically interact with the Pioneer spacecraft. Section 6, the heat shield hypothesis, a closer look at the spacecraft. While exotic hypotheses involving dark matter and extra dimensions captured the imagination, a more mundane explanation emerged from a closer examination of the Pioneer spacecraft themselves. This explanation, known as the heat shield hypothesis, focused on the thermal properties of the spacecraft and their potential influence on its trajectory. The Pioneer spacecraft were equipped with radioactive plutonium-238 thermoelectric generators, or RTGs, to provide electrical power. These RTGs generated heat as a byproduct of their operation. Some scientists hypothesized that the heat emitted by the RTGs, particularly from the spacecraft's conical heat shield, could create a tiny but persistent thrust. This thrust, known as thermal recoil force, arises when heat radiating from an object is not emitted uniformly in all directions. In the case of the Pioneer spacecraft, it was proposed that the heat shield's geometry could cause a net thermal recoil force directed towards the Sun, potentially explaining the observed anomaly. Section 7. The anomaly explained, the prevailing theory. The heat shield hypothesis gained traction as scientists conducted detailed thermal modeling of the Pioneer spacecraft. These models took into account the geometry of the spacecraft, the properties of the materials used in their construction, and the heat generated by the RTGs. The models revealed that the thermal recoil force generated by the heat shield, while small, was indeed in the right direction and of the right magnitude to account for a significant portion of the observed anomaly. This finding provided the most plausible explanation for the Pioneer anomaly to date. Further support for the heat shield hypothesis came from the analysis of data from other spacecraft, such as the Ulysses and Cassini missions. These spacecraft, which had different designs and thermal properties than the Pioneer spacecraft, did not exhibit the same level of anomalous acceleration. Section 8. Lingering uncertainties. The debate continues. While the heat shield hypothesis emerged as the leading explanation for the Pioneer anomaly, some uncertainties and debates persist. The thermal models, while sophisticated, rely on assumptions about the spacecraft's thermal properties and the behavior of materials in the space environment. Some scientists argue that the uncertainties in these models are still too large to definitively conclude that the heat shield hypothesis fully explains the anomaly. They point to the fact that the models cannot account for the entirety of the observed acceleration, leaving room for other, potentially unknown factors to be at play. Furthermore, the Pioneer anomaly has reignited discussions about the accuracy of our understanding of gravity itself. Some physicists have proposed modifications to Newton's law of gravity or Einstein's theory of general relativity as potential explanations for the anomaly. Section 9. The Pioneer Anomaly's Legacy Advancing Space Exploration. The Pioneer Anomaly, despite its eventual explanation, has left an indelible mark on space exploration. The decades-long quest to understand this cosmic puzzle has led to advancements in our understanding of spacecraft design, thermal modeling, and the behavior of objects in the space environment. The anomaly has also highlighted the importance of precise measurements and meticulous data analysis in space missions. The tiny discrepancy in the Pioneer spacecraft's trajectories, initially dismissed as insignificant, ultimately revealed a fascinating scientific mystery. Moreover, the Pioneer anomaly has served as a reminder that our universe still holds mysteries, pushing the boundaries of our scientific knowledge and inspiring new generations of scientists and engineers. Section 10. Future missions and the quest for knowledge. The Pioneer anomaly, though largely explained, continues to motivate future space missions and technological advancements. Scientists are eager to design missions that can more accurately measure the trajectories of spacecraft and test the limits of our understanding of gravity. One such mission concept involves sending a dedicated spacecraft equipped with advanced tracking systems and thermal control mechanisms to the outer solar system. This spacecraft would be designed to minimize any potential thermal recoil forces, allowing scientists to more precisely measure any anomalous accelerations. Furthermore, advances in data analysis techniques, such as machine learning, could help scientists sift through vast amounts of data from current and future space missions to search for subtle anomalies that might provide clues about new physics or unknown phenomena. The enduring allure of the cosmos. The Pioneer anomaly stands as a testament to the allure of the cosmos and scientific inquiry. A perplexing discrepancy in the trajectory of two spacecraft launched over 4 decades ago captivated scientists and the public. This cosmic mystery led to advancements in spacecraft design and thermal modeling. Lingering uncertainties remind us that our universe still holds mysteries. As we venture further, new mysteries will emerge, challenging our assumptions.